If the determinant of this 4 by 4 matrix is 150, then calculate the determinant of this 4 by 4 matrix. It's difficult to solve this question unless we have a knowledge about properties of determinant. Hence, to solve this question and other related questions, let's see some of the properties of determinants. The first property, determinant of matrix A equal to determinant of its transpose. The determinant of this 3 by 3 matrix is equal to the determinant of its transpose. How can we find its transpose? Just by interchanging rows and columns of the given matrix, meaning row 1 becomes column 1, row 2 becomes column 2, and row 3 becomes column 3. Another example, the determinant of this 3 by 3 matrix, of which its elements are designated by numbers, is equal to the determinant of its transpose. As usual, the transpose can be determined by interchanging rows and columns, meaning column 1 becomes row 1, column 2 becomes row 2, and column 3 becomes row 3. The second property, if matrix B is found by interchanging two rows or columns of matrix A, then the determinant of matrix B equal to negative of the determinant of matrix A. For example, if matrix A equal to this 3 by 3 matrix and matrix B equal to this 3 by 3 matrix, then the determinant of matrix B equal to negative of the determinant of matrix A. Why? To figure out the reason, let's analyze the two matrix elements. A in the first row, first column of matrix A becomes in the first row, third column of matrix B. 3x in the second row, first column of matrix A becomes in the second row, third column of matrix B. S in the third row, first column of matrix A becomes in the third row, third column of matrix B. This shows us that column 1 of matrix A becomes column 3 of matrix B. If you analyze column 3 of matrix A, it becomes column 1 of matrix B. In other words, matrix B is found by interchanging column 1 and column 3 of matrix A. That's why the determinant of matrix B equal to negative of the determinant of matrix A. The determinant of this 3 by 3 matrix is equal to the negative of the determinant of this second 3 by 3 matrix. Why? Because this second 3 by 3 matrix is found by interchanging row 1 and row 3 of the first 3 by 3 matrix. Again, from this second 3 by 3 matrix, if we interchange column 1 and column 3, its determinant is equal to the determinant of the first 3 by 3 matrix, because negative times negative gives us positive. What I mean is, when we interchange row 1 and row 3, we multiply the determinant by negative. Again, when we interchange column 1 and column 3, of which its determinant is already multiplied by negative, we have to multiply it by negative in order to find the determinant of this new 3 by 3 matrix. Thus, negative times negative gives us positive. The third property, if matrix A has row or column of zeros, then the determinant of matrix A equal to 0. When we say row or column of zeros, we mean that if all elements of a given row or column are 0, the determinant of this 4 by 4 matrix is equal to 0 because all row 3 elements are zeros. In similar manner, the determinant of this second 4 by 4 matrix is equal to 0 because all column 2 elements are 0. Also, the determinant of this third 4 by 4 matrix is 0 because all row 2 and column 3 elements are zeros. The determinant of this 3 by 3 matrix is also equal to 0 because all of its third column elements are zeros. The fourth property, if matrix A has identical rows or columns, then the determinant of matrix A equal to 0. The determinant of this 2 by 2 matrix is equal to the determinant of this 3 by 3 matrix. Again, it is equal to the determinant of this 4 by 4 matrix, which is equal to 0. Why? Because two rows or two columns of either of these matrices are identical. In the first matrix, row 1 and row 2 are identical, or we can also say that column 1 and column 2 are identical. In the second matrix, column 1 and column 3 are identical, and in this third matrix, row 1 and row 4 are identical. Property 3 and property 4 are straightforward properties because What we are expected to do is just to check whether any row or column with all elements zeros or any row or column with identical elements. If it's so, the determinant is equal to 0. The fifth property, if matrix B is found by adding a multiple of row or column of matrix A to another row or column of matrix A, then the determinant of matrix B equal to determinants of matrix A. If matrix A equal to this 3 by 3 matrix and matrix B equal to this 3 by 3 matrix, then the determinant of matrix B equal to determinant of matrix A. Why? If we analyze matrix A and matrix B, we will find that row 1 of matrix A equal to row 1 of matrix B, and row 3 of matrix A is the same as row 3 of matrix B. The only difference is in row 2. Row 2 column 1 of matrix A is 1, but row 2 column 1 of matrix B is 7. Putting the given relationship in mind, let's figure out the mathematical relationship between these two numbers. That's between 1 and 7. 7 means either 3 times the first element of row 1, that's 2 plus 1, or the first element of row 3, that's 6 plus 1. We can draw a number of relationships, but for the time being, let's pick only these two. When we move to row 2 column 2 entry, row 2 column 2 of A is 4, but row 2 column 2 of B is 13. 13 means 3 times the second element of row 1, that's 3 plus 4. But the second element of the third row, that's 7 plus 4, is not equal to 13. Rather, it's 11. So this relationship doesn't work. When you come to row 2 column 3 elements, row 2 column 3 of matrix A is 8, and row 2 column 3 of matrix B is 23. 23 means 3 times the third element of first row, that's 5 plus 8. So the mathematical relationship that transforms row 2 of matrix A to row 2 of matrix B is 3 times first row elements of matrix A plus second row elements of matrix A. As we defined, if a matrix is obtained by adding a multiple of row or column of a matrix to another row or column of the same matrix, then the determinant of the two matrices are equal. By the same analogy, the determinant of this 4 by 4 matrix is equal to the determinant of this 4 by 4 matrix. Row 3 of this right hand side matrix is equal to row 3 of the left hand side matrix plus 2 y's of row 4. The determinant of this 3 by 3 matrix is equal to the determinant of this 3 by 3 matrix. Column 1 of the left hand side matrix is equal to column 1 of the right hand side matrix, and column 2 of the left hand side matrix is also equal to column 2 of the right hand side matrix. But column 3's are different. So let's find the relationship between column 3 of the right hand side matrix with column 3 of the left hand side matrix and one other column of the left hand side matrix. 0 means either 4 times negative 1 plus 4 or 6 times negative 2 over 3 plus 4. 21 means 4 times 5 plus 1, but 8 times negative 2 over 3 plus 1 doesn't give us 21. So this second relationship doesn't work. 39 means 4 times 9 plus 3. These relationships tell us that column 3 of the right hand side matrix is obtained by adding 4 times column 1 of the left hand side matrix and column 3 of the left hand side matrix. That's why the determinant of the two matrices are equal. The sixth property, if matrix B is found by multiplying one row or one column of matrix A by scalar R, then the determinant of matrix B equal to the scalar R times the determinant of matrix A. If matrix A equal to this 3 by 3 matrix and matrix B equal to this 3 by 3 matrix, then determinant of matrix B equal to 1 over 4 times determinant of matrix A, because row 1 of matrix B is found by multiplying row 1 of matrix A by 1 over 4, keeping that row 2 and row 3 are similar. What's the relationship between the determinant of these two matrices? These 4 elements at the left are equal to the corresponding elements at the right. First row, first column at the left equal to 4 times first row, first column at the right. First row, second column at the left equal to 12 times first row, second column at the right. First row, third column at the left equal to 4 times first row, second column at the right. Second row, second column at the left equal to 3 times second row, second column at the right. Third row, second column at the left equal to 3 times third row, second column at the right. Now we discover that row 1 and column 2 are the row and column multiplied by a certain constant. This y is a junction between row 1 and column 2. That's why it's multiplied by 12, because 12 means 4 times 3. 4 is a constant we use to multiply row 1 elements, and 3 is a constant we use to multiply column 2 elements. Thus, the determinant of this left-hand side matrix is equal to the scalar we use to multiply row 1, that's 4, times the scalar we use to multiply column 2, that's 3, times the determinant of the right-hand side matrix, which is equal to 4 times 3 is 12 times the determinant of the right-hand side matrix. If we have a knowledge about these properties, we can easily solve the question we are asked at the beginning of this section. The question is this. Let's rewrite the elements of this right-hand side matrix as a certain constant times the elements of this left-hand side matrix. Let's start from row 1. This 2a means 2 times a, 4b means 2 times 2b, 12c means 6 times 2c, and negative 2d means 2 times negative d. Row 2 to row 4 elements are the same except those under column 3. So let's rewrite column 3 elements of the right-hand side matrix as the product of a certain constant times the corresponding column 3 elements of the left-hand side matrix. Let's copy the other elements as they are. First row of column 3 is as it is, that's 6 times 2c. Negative 6c means 3 times negative 2c. Negative 3c means 3 times negative c. And 3c means 3 times c. The element as the junction is 6 times 2c. 6 means 2 times 3. At this stage, we figure out the constants that multiply row 1 and column 3 of the given matrix. These are 2 for row 1 and 3 for column 3. Therefore, the determinant of this right-hand side matrix is equal to the scalar that multiplies row 1, that's 2, times the scalar that multiplies column 3, that's 3, times the determinant of the given matrix, that's 150. 2 times 3 is 6. 6 times 150 is 900. Let me add one more question. If the determinant of this 4 by 4 matrix is equal to 50, then calculate the determinant of this 4 by 4 matrix. Let's take the right-hand side matrix and write in terms of the given matrix. Row 1, row 3, and row 4 elements are the same, so we can copy them as they are. The difference is in row 2 only. Row 2 elements in the question can be expressed as twice of row 1 elements plus the corresponding row 2 elements of the given matrix, meaning 5a means 2 times a, that's 2a plus 3a. 4b means 2 times b, that's 2b plus 2b. 5c means 2 times 2c, that's 4c plus c. And negative d means 2 times d, that's 2d plus negative 3d. From this expression, we can understand that these row 2 elements are obtained by adding twice of row 1 elements to the corresponding row 2 elements of the given matrix. As we discussed above, if a matrix is obtained by adding a multiple of row or column of a certain matrix to another row or column of the same matrix, then their determinant is equal. Thus, the determinant of these two matrices are equal, that's 50. This brings the end of this section. Please subscribe, like, and share the page. Thank you for your attention. Bye-bye.